Our second video in the thermodynamics series covers the topic of entropy. This will focus on the objective of evaluate data to determine entropy change and energy flow. First of all, as a review, I want to be clear on what spontaneous means. If a process occurs without outside intervention, it is said to be spontaneous. The speed of that process is irrelevant for this topic. The example I use in the slide is that of a rusting car. If exposed to air and moisture, steel rusts spontaneously. However, the reverse reaction of the iron oxide and rust does not spontaneously change back to iron metal and oxygen gas. So reactions are spontaneous in one direction, but not in the other. The idea of spontaneity has actually evolved a bit over time. It was once believed that a reaction would be spontaneous if it were exothermic. And this is a really important component to it, but it is a little more involved than what was first thought. For example, it does not explain how ice melts spontaneously at temperatures greater than 0 degrees, even though this is an endothermic process. The other main driving force behind spontaneity is entropy, which is represented by S in an equation. Entropy can be viewed as a measure of molecular randomness or disorder. Even though it is often described as the amount of chaos, I encourage you not to use this definition. It has more to do with randomness and positional probability, which we will discuss later, than the idea of chaos. The natural progression of things is from order to disorder, from a lower entropy to a higher entropy. And the analogy I always use here is your room. The natural progression is for your room to become disordered and messy. It takes more effort to keep your room ordered. But more specifically, entropy is a thermodynamic function that describes the number of arrangements, or positions, and energy levels that are available to a system existing in its given state. Entropy is closely associated with probability. Nature spontaneously proceeds towards the state that has the highest probabilities of existing. Because of this, entropy has a lot to do with changes of state, because changes of state illustrate positional probability. In general, positional entropy increases in going from a solid to a liquid to a gas. In a solid state, molecules are close together with relatively few positions available to them. In a gas state, the molecules are far apart with many more positions available. For example, when looking at a solid, it has specific arrangements of atoms. Ionic compounds and metals form crystal structures, and the overall arrangement is very ordered. But in a liquid state, the atoms or molecules are less ordered. They have the ability to move around each other and are not stuck in one position. Therefore, they have more positional probability. Finally, the gases have atoms or molecules that are in random motion and random positions at any given time. Gases have the most positional probability. Therefore, positional probability and entropy increase as physical states change from a solid to a liquid and liquid to a gas. There is another way that a substance can gain positional probability. Entropy changes with the mixing of two pure substances and is expected to be positive. For example, when two liquids are mixed to form a solution, the molecules of each liquid have more total available volume and thus more available positions. Let's look quickly at two example problems. Example problem number 14 is on page 778 in your textbook. For each of the following pairs, choose the substance with the higher positional entropy per mole at a given temperature. The first one is solid CO2 or gaseous CO2. In this case, the molecules in the gas state have a lot more positional probability than that of the solid. So the gaseous CO2 has higher entropy. For the second one, N2 gas at 1 atmosphere, or N2 gas at 1 times 10 to the negative second atmosphere. The gas under less pressure has more room to move around and therefore has more positional probability, and in this case, more entropy. Let's try one more. Predict the sign of the entropy change for each of the following processes. The first one, solid sugar is added to water to form a solution. As a solid dissolves, positional probability increases. This is a positive change in entropy. The second one, iodine vapor condenses on a cold surface to form crystals. Vapor, which is in its gaseous state, has a lot more positional probability than that of the solid that it is forming. The entropy change in this case is negative. This concludes the last of the entropy video, but we will discuss the applications of entropy a little bit more in class.